Hello everyone. I hope you guys can hear me. Uh, so last time I was studying about vector valued functions. I do need some more practice on that. I studied it last stream. Well, I did more revision last stream. This stream I'm going to start the next chapter. Hold on. Yeah. So last stream I finished this. Well, I say finished, I mean I read this. Motions in space was the last topic. And this time I'm going to be studying differentiation of functions of several variables. Okay. I'll just hide this. In Introduction to Applications of Derivatives, we study how to determine the maximum and minimum of a function of one variable over a closed interval. This function might represent the temperature over a given time interval, the position of a car as a function of time, or the altitude of a jet plane as it travels from New York to San Francisco. In each of these examples, the function has one independent variable. Suppose, however, that we have a quantity that depends on more than one variable. For example, temperature depends on location and time of day, or a company's profit model might depend on the number of units sold and the amount of money spent on advertising. In this chapter, we look at a company that produces golf balls. We develop a profit model, and under various restrictions, we find that the optimal level of production and advertising dollars spent determines the maximum possible profit. When dealing with a function of more than one independent variable, several questions naturally arise. For example, how can we calculate the limits of functions of more than one variable? Okay, next chapter. So, functions of two variables. The definition of a function of two variables is very similar to the definition for a function of one variable. The main difference is that instead of mapping values of one variable to values of another variable, we map ordered pairs of variables to another variable. A function of two variables, so f of x and y, maps each ordered pair xy in a subset D, so the domain space, of the real plane R squared to a unique real number Z. Okay. The set D is called the domain of the function. The range of f is the set of all real numbers that has at least one ordered pair, such that f of xy is equal to Z as shown in the figure below. Determining the domain of a function of two variables involves taking into account any domain restrictions that may exist. Let's take a look. So domain and ranges for a function of two variables. Find the domain and range of each of the following function. So x, y. I'm guessing x and y can be any real number. I mean, it can be complex also. So if x and y are both real numbers, then the output is also a real number, right? There are no values or combinations of x and y that causes f of x, y to be undefined. So the domain of f is R squared. To determine the range, first pick a value for z. We need to find a solution to the equation f of x, y is equal to z, or 3x plus 5y plus 2 is z. One such solution can be obtained by first setting y is equal to 0, which yields the equation 3x plus 2 is equal to z. The solution to this equation is x is equal to z minus 2 over 3, which gives the ordered pair this as a solution to the equation f of x, y, z for any value of z. Therefore, the range of the function is all real numbers, or R. For the function g, x, y to have a real value, so this has to be positive, right? So x and y are any real number, and inside the square root, it has to be positive. The quantity under the square root must be non-negative. This inequality can be written in this form. Therefore, the domain of G is x, y, all real numbers such that this is satisfied. X squared plus y squared is less than or equal to 9. The graph of this set of points can be described as a disk of radius 3 centered at the origin. The domain includes the boundary circle as shown. Okay, so these are all the numbers here are capable of being x or y, and it includes the circle as well. The range of this function can be written in interval notation as 0 and 3. Suppose we wish to graph the function z is equal to x, y. This function has two independent variables, x and y, and one dependent variable. When graphing a function y is equal to f of x of one variable, we use the Cartesian plane. We are able to graph any ordered pair in the plane, and every point in the plane has an ordered pair associated with it. With a function of two variables, each ordered pair in the domain of the function is mapped to a real number z. Therefore, the graph of the function f consists of the ordered triplets x, y, z. The graph of a function z is equal to x, y of two variables is called a surface. To understand more completely the concept of plotting a set of ordered triplets to obtain a surface in three-dimensional space, imagine the xy coordinate system laying flat. Then every point in the domain of the function has a unique z value associated with it. If z is positive, then the graphed point is located above the xy plane. Doesn't Desmos have like a 3D graph? Yeah, it does. Let's see. So xy will be the independent, z will be the output. Uh, to understand more completely the concept of plotting a set of ordered triplets to obtain a three-dimensional space, imagine the xy system coordinate system laying flat. So xy over here. Then every point in the domain of f has a unique z value associated with it. So let's see, x, y, z. How do you define? So in Desmos, we can do like f of x, like in the 2D calculator, we can do f of x is equal to y, but how do you do? Maybe 5x plus 3y squared. Okay, cubed. Can I make it transparent? I don't think we can. This is still new though. So what were they saying? If z is positive, then the graphed point is located above the xy plane. Yeah. If z is a positive value, then it will be above the xy plane. If it's negative, then it will be below. Okay. Create a graph of each of the following functions. Let's try x squared plus y squared. Square, square. Oh, it's like a parabola, right? A profit function for a hardware manufacturer is given by this equation, where x is the number of nuts sold per month and y represents the number of bolts sold per month. Both are measured in thousands. profit is measured in thousands of dollars. Sketch a graph of this function. Okay, I won't be sketching. I will just. So 16 x minus 3 square, y minus 2 square. Would it be like a sphere? 16 minus x minus 3 square minus y minus 2 x minus 3 y minus 2. Okay, so it's not a sphere. This is also like a parabola. And since it's like dollars, assuming they would both be positive, right? So this is only defined when z is positive. Or wait, hold on. Represents the number of balls sold per month. How do I write conditions? Y more than 0. Yeah. And then x more than 0 maybe. How do you write multiple conditions? Okay, so y is more than 0 and x also. Nope. X is more than equal to 0. Yeah. The graph looks like this, but z also has to be more than 0, right? Wait, if the number of nuts and bolts is 0, we would be left with 16. But where is he getting profit of 16 if he didn't sell any of these two? If hikers walk along rugged trails, they might use a topographical map that shows how steeply the trail changes. A topographical map contains curved lines called contour lines. Each contour line corresponds to the points on the map that have equal elevation. A level of curve of a function of two variables is completely analogous to a contour line on a topographical map. A topographical map of Devil's Tower, Wyoming. Lines that are close together indicate a very steep terrain. A perspective photo of Devil's Tower shows just how steep the slides are. Notice the top of the tower has the same shape as the center of the topographical map. Given a function and a number c in the range of f, a level of curve of a function of two variables for the value c is defined to be the set of points satisfying the equation f of x y is equal to c. Returning to the function gxy, we can determine the level of curves of this function. The range of g is a closed interval. First, we choose any number in this closed interval, say 2, say c is 2. The level curve corresponding to c is equal to 2 is described by the equation. Okay, so they're setting the boundary where the output is 2. So I guess instead of like this, let's remove the condition. Instead of this, we would have like lines representing where the intersection points are. What else can we interference? Let's say z is 5. How do we? I only want to show the intersection though. I think I would have to use some other 3D graph. Okay, this is for translucent. I think the other one is better. Anyways, okay, so counter lines. So here they're showing the counter of 0, 1, and 2. Hold on a minute. If I do x square plus y square equals 5, let's drop this line. 5, 0, 2, 1, 3, 4, 5. 9. It would get bigger, right? So if the value of c is bigger, shouldn't? Hold on. No, it's subtracting. No, it's different. Square root. Nine minus 0. 2, 1.5. Is it even defined at 0? Like if this gets squared and then it becomes minus 9. Yeah, I think now I understand. Smaller values, bigger circle. Anyways, given the function xy, this find the level of curve corresponding to c is equal to 0, then create a contour map for this function. What is the domain and range of f? Okay, let's copy. This is from last stream. I will just reset the canvas. Paste. What exercise is this? 4.4. Example 4.4. So f of xy is all this, and then they're equating it to c. 8 plus 8x minus 4y minus 4x square plus y square is 0. We square both sides. We are left with this. Now what? Hold on. If I do y, 2y plus 2, there's no xy, right? 2x plus 2. Hold on. If I do this, I'll get 4x squared, 4x, 4x. I'll be left with 8x plus 4. If one of them is minus, then I'll be left with minus 4 squared minus 4x. And then hold on. Let me think about this. If it was like this, I would have 4x squared minus 4x minus 4x, so minus 8x plus 4. If I have y minus 2, y minus 2, y square minus 4y. Let's see. Y square minus 4y plus 4. If I add these two together, I'll be left with 4x square minus 8x plus 4. It's close, but not what I was searching for. What did they do? We then square both sides and multiply both sides of the equation by minus 1. If we multiply both sides of the equation by minus 1, we are left with minus plus 4y plus 4x plus y squared. Then if this is minus, this is plus. It's not going to make a difference, I think. Now we arrange the term, putting x term together and the y terms together. Now we group them. Then we complete the square in each parenthesis and add the correct value to the right hand side. Yeah, I don't understand what they did. Divided by 16, we are left with this. This equation describes an ellipse centered at 1 and minus 2. The graph of the ellipse appears on the following graph. And then they added the contours. We can repeat the same derivation for values of c less than 4. So the domain xy inside this ellipse, the range is 0 to 4. Another useful tool for understanding the graph of a function of two variables is called a vertical trace. Level curves are always graphed in the xy plane, but as their name implies, vertical traces are graphed in the xz or xyz planes. Consider a function z is equal to f of xy with domain r square. A vertical trace of the function can be either the set of points that solves the equation f a y z, or a constant x is equal to a, or f of x b is equal to c for a given constant y is equal to b. A vertical trace. So we keep one of the two constant and we see, like we check the graph when one of them is a constant, like, oh wait, I think for example in here it would be like, instead of y we have 5 or 1, y we have, yeah, 1. I think this is what they mean by vertical trace. We have like one slice of the entire graph. That slices when y is equal to 1. Can change it to, let's say, zero point 0.5. Yeah. Find vertical traces for the function y is equal to xy sine x cos y, corresponding to x is minus pi over 4, 0 and pi over 4, and y is equal to minus pi over 4, 0 and pi over 4. So they just, like, for x is equal to minus pi over 4, you just put the value of minus pi over 4. And wait, what was sine pi over 4? Sine pi over 4 minus pi over 4. Wasn't this, yeah, root 2 over 2. So root 2 over 2 is in minus. Yeah, minus root 2 over 2 cos x, cos y. That's the graph you will be left with. Vertical traces for x is equal to c. We have x, z is minus 2 root 2 over 2 cos y, z is 0, and root 2 over 2 cos y. Okay. Yeah, they have like slices of the graph. Functions of two variables can produce some striking looking surfaces. The following figure shows two examples. Uh, okay. So far, we have examined only functions of two variables. However, it is useful to take a brief look at functions of more than two variables. Two such examples are f of x, y, z, a polynomial in three variables, and g is g of x, y, and t. In the first function, x, y, and z represents a point in space, and the function f maps each point in space to a fourth quantity, such as temperature or wind speed. In the second function, x, y can represent a point in the plane, and t can represent time. The function might map a point in the plane to a third quantity, like pressure, at a given time t. The method for finding the domain of a function of two more than two variables is analogous to the method for functions of one or two variables. Domains for functions of three variables. So the numerator can be anything, but the denominator, there's a square root. This is an issue. So 9 minus x square minus y square minus z square. And this is example 4.6. So root 9 minus x square y square z square. This has to be positive, right? So then we can write it like this also. 2. And if we do minus, the sign changes. So I'm guessing this is the domain, right? And the largest quantity, like say this x, y, and z, all of them are 0. Then root 9 is positive 3. The largest value of this can be positive 3, right? So the range is from negative 3 to positive 3. So domain is where all of these are less than 9. If they're equal to 9, wouldn't that also count? Functions of two variables have level curves which are shown as curves in the xy plane. However, when the function has three variables, the curve becomes surfaces. So we can define level surfaces for functions of three variables. Given a function f of x, y, z and a number c in the range of f, a level surface of a function of three variables is defined to be a set of points satisfying the equation f of x, y, z is equal to c. It's like counterpoint, but like for three dimensions. A level surface. What do we call it before? We just call it contour lines, right? A level curve. Okay. A level surface and a level curve. Find the level curve for the function this corresponding to c is equal to 1. So example 4.7. Let me just delete this because it takes up memory. So we have 4 squared 9. This has to be 1, right? So what are we trying to find? Find the level surface for this one. Isn't this it? Or they wanted to graph it. This equation describes a hyperboloid of one sheet as shown in the following figure. So this is C0, C1, C2, C3. So the entire thing is in the fourth dimension, right? The output is in the fourth dimension. Recall from the limit of a function the definition of a limit of a function of one variable. Let f of x be defined for all uh, x is not a in an open interval containing a. Let L be a real number. Then limit as x approaches a, f of x is equal to L is approaches L. If for every epsilon more than 0 there exists a delta more than 0 such that if x minus a is less than delta for all x in the domain of f, then f of x minus L is less than sigma. Before we can adapt this definition to define a limit of a function of two variables, we need to first see how to extend the idea of an open interval in one variable to an open interval at two variables. And before I do that, uh, limit of a function, let's say it's continuous in an open interval containing a but not equal to a. If we have a over here, x over here, and we bring x closer to a from either side. So limit x approaches a. This is f of x. So x doesn't touch a, there's always some distance. So now we start with if, yeah, and this over here is L. So like, and one more, this over here is f of x, x1, x1. So you can think of try to think of any sigma more than 0, then there will always exist a delta such that if there's a distance of delta between these two, distance of at least delta. Yeah, think of any sigma, there will always be a delta such that if the distance between them is less than delta, then the distance between these two will be less than sigma. So 0 distance between them is less than delta, then distance between minus L will be less than sigma. That's the definition of a limit. Consider a point AB. Consider a point AB. Delta disk centered at point AB is defined to be an open disk of radius delta centered at point AB, that is xy, which can be any real value, such that this condition is true. So they're defining these points. The idea of a delta disk appears on the definition of limit of a function of two variables. If delta is small, then all points xy in the disk space are close to B. In more than one dimension, we use the delta disk. So let f be a function of two variables, x and y. The limit of f of xy as xy approaches ab is L. So limit xy approaches ab. Okay. If for each epsilon more than if for each epsilon there exists a small enough delta such that for all points xy in a delta disk around AB, except possibly for AB itself, the value of f of xy is no more than epsilon away from L. Using symbols, we can write the following. So this is less than epsilon. So there's always some distance. Whenever there's always some distance over here. Okay, so this is on the surface. And yeah, if AB is within the disk, then L will be within less than like epsilon. There will always be a distance between f of xy and L. Proving that a limit exists using the definition of a limit of a function of two variables can be challenging. Instead, we use the following theorem, which gives us shortcuts to finding limits. The formulas in this theorem are an extension of the formulas in the limit law, in the limit laws theorem in the limit laws. So let f x y g x y be defined for all x y not a b in a neighborhood around a b, and assume the neighborhood is contained completely inside the domain of f. Assume that L and M are real numbers such that limit xy approaching a b goes to L and limit xy approaching a b goes to M. Let c be a constant. Then each of the following statements hold. Okay, so constant law, identity law, sum law, difference, constant multiple. So I'm guessing most of the identity would hold. The proof for these properties are similar to those for the limits of functions of one variable. You can apply these laws for to finding limits of several variables. For each of the find each of the following limit. Okay, let's see. Did not copy properly. Don't know why this one gets slow sometimes. See. Example 4.8. So the limit would just be 2 square minus 2 to negative 1. Just substitute the values, right? Using the limit laws. Minus 4 to plus 3 minus 1, then minus 6. So 2 square, I'm still looking here though. 4 minus, it becomes plus, so plus 4. And then what? Minus 1 squared, so that just becomes 3. Now 4 times 2, 8. Minus 3 minus 6. So this and this cancel, this and this cancel. We are left with minus 6. Yeah. Before applying the quotient law, we need to verify that the limit of the denominator is non-zero using the difference law, constant multiple law, and identity law. They found 11. Limits that fail to exist show that neither of the following limits exist. So x, y, 0, 0. It's undefined at this point. However, do we do that limit from the right side and limit from the left side thing? Because for a limit to exist, yeah, both of these goes to the denominator is 0. Consider the line y is equal to 0 in the xy plane. Substituting y is equal to 0 in f of xy gives this for any value of x. Therefore, the value of f remains constant for any point on the x-axis, and y approaches as y approaches 0, the function remains fixed at 0. Next, consider the line y is equal to x. Substituting y is equal to x into f of xy gives this. This is true for any point on the line y is equal to x. If we let x approach 0 while staying on this line, the value of the function remains fixed at half regardless of how small x is. Choose a value epsilon that is less than half, say 1 over 4. Then no matter how small delta disk we draw around 0, 0, the values of f of xy for points inside that disk will include 0 and half. Therefore, the definition of the limit at a point is never satisfied and the limit fails to exist. To study continuity and differentiability of a function of two or more variables, we first need to learn some new terminology. Let S be a subset of R squared. A point P naught is called an interior point of S if there is a delta disk centered around a P naught contained completely in S. Mm, A point P naught is called a boundary point of S if delta disk centered around P naught contains point both inside and outside S. If every delta disk. S is called an open set if every point of S is an interior point. S is called a closed set if it contains all its if it contains all its boundary points. An example of an open set is a delta disk. If you include the boundary of the disk, then it becomes a closed set. A set that contains some but not all of its boundary sets is neither open nor closed. For example, if you include half the boundary of a delta disk but not the other half, then the set is neither open nor closed. An open set S is a connected set if it cannot be represented as a union of two or more disjoint non-empty open subsets. A set S is a region if it is open, connected, and non-empty. An open set S is a connected set if it cannot be represented as a union of two or more disjoint non-empty open subsets. I need more clarification on the first part. Okay, so if the boundary is not included as part of the set and non-open, non-empty, then it's a region. If it cannot be represented as the union of two or more disjoint non-empty open subset. Okay, I need more clarification on the first one. The definition of a limit of a function of two variables requires the delta disk to be contained inside the domain of the function. However, if you wish to find the limit of a function at a boundary point of the domain, the delta disk is not contained inside the domain. By definition, some of the points of the delta disk are inside the domain, some of the points are outside. Therefore, we only need to consider points that are inside both the delta disk and the domain of the function. This leads to a definition of a function at a boundary point. Let f be a function of two variables, x and y. And suppose ab is on the boundary point of the domain of f. Then the limit of f of xy as xy approaches ab is L, written like this. If for every sigma there exists a delta such that any point xy inside the domain of f and within a suitable small distance positive delta of ab, the value of f xy is no more then delta away from L. Using symbols, we can write for any sigma, there exists a delta such that f of xy minus L less than sigma whenever all of this is less than delta. limit of a function at a boundary point. So prove this. So if for any sigma there exists a number delta such that for any point xy inside the domain of f and within a suitable distance positive delta, the value of f of xy is no more than sigma away from L. Okay, for this, I think we should need to calculate where it can't be defined. So, wait, this is wrong. So prove this. Yeah, 4, 3. Limit so let's say so the domain of this is if the inside is more than 0. And then 25. So this has to be less than 25. So the domain is that x, y within the subset R squared, given that x squared, y squared is less than 25. And then range is some xy root 25 is plus minus 5, right? So I guess this is the range. So limit 4, 3. So 4 squared plus 3 squared is 25. But how do you prove the limit? That's what I don't understand. I mean, we can substitute it in, but we can substitute 4 and 3 in to show that it's 0. You can substitute any value of x or not. So first we can do this. 4 square minus 3 square is 0. And then for y less than, actually, for any sigma, uh, isn't the notation, isn't the notation like this? For all sigma, there exist a delta such that L is 0, right? Such that f of x, y is more than 0. So the limit it approaches 0. Let's say there's some distance between f of x, y and 0. Then x and y is in a disk of size delta centered at AB. Centered at 4, 3. This is what we are trying to prove, right? Doesn't need to be 0. This has to be sigma. The distance between f of xy and 0. So basically, if f of xy has any value more than 0, more than sigma. The domain is this, which is a radius of 5 centered at the origin. Okay. You can use limit laws, which applies to the limits at the boundary as well as the interior. The limit laws, this is 0. So all they did was substitute it. Like, shouldn't they only do it within the boundary? In continuity, we define the continuity of a function of one variable and saw how it relied on the limit of a function of one variable. In particular, three conditions are necessary for f of x to be continuous at point x is equal to a. F of a exists, limit as x approaches a at f of x exists, limit as x approaches a at f of x is equal to f of a. Okay, so continuity is like, you cannot have a function that's like this. You cannot have any jumps or like this. The function has to be defined at this point. Okay, this is ugly. The function has to be defined at that point, and the limit should exist. So what does it mean for the limit to exist? So let's say the function is this, defined at this point, not defined here. So the limit doesn't exist because the left limit and right limit are different. So this needs to be valid. This number 2 needs to be valid. And then number 3. Wait, I have a question. Yeah, Actually, if I have something like this not defined here, but at this point, it's like over here. So f of x is defined, but for this point, there's like a jump. This violates the third point because the limit is defined, limit on right side and left side going to the same point. So the limit is defined. F of x is defined because it has a value at that point. However, the value and the limit, they're like different. The actual value and the limit are different. So that violates the third point. So all these 3 points need to be valid in order for the function to be continuous at that point. A function f of x, y is continuous at point A, B in its domain if the following conditions are satisfied. Okay. So it's just like with one variable then. Continuity of a function of any number of variables can also be defined in terms of delta and epsilon. A function of two variables is continuous at a point x naught, y naught in its domain for every sigma more than 0. If for every sigma more than 0 there exists a delta such that whenever this is less than delta, it is true, then this will be less than epsilon. This definition can be combined with a formal definition of continuity of a function of one variable to prove the following theorem. The sum of a continuous function is continuous. Okay. The product of a continuous function is continuous. The composition of a continuous function is continuous. All right. More examples of continuity of a function of two variables. Show that functions f of x, y, g of x, y are continuous everywhere. Okay, so f of x, y, it's defined for all a, b. The domain is like the all real number squared. So for all x and for all y. So the first condition is met. The first condition is met. The second condition, so the limit exists, that is met, and so is the third condition. But how do you prove polynomials g 4x cubed and hy is y squared are continuous at every real number? Therefore, the product of continuous function theorem is continuous at every point in the xy plane. Since f of x y is equal to 4x cubed y squared is continuous at every point in the xy plane, and g x cos x is continuous at every real number, the continuity of the composition of function tells us that g x y cos 4x cubed y squared is continuous at every point in the xy plane. The limit of a function of 3 or more variables occur readily in applications. For example, suppose we have function xyz that gives the temperature of a physical condition in 3 dimensions. Or perhaps the function xyzt can indicate air pressure at location xyz at time t. How can we take a limit at a point in R cubed? What does it mean to be continuous at a point in 4 dimensions? The answers to these questions rely on extending the concept of a delta disk into more than 2 dimensions. Then the ideas of limit of a function of 3 or more variables and the continuity of a function of 3 or more variables are very similar to the definition of given earlier for a function of 2 variables. So let x naught, y naught, z naught be a point in R cube. Then delta ball in 3 dimensions consists of all points in R-cube lying at a distance less than delta from x naught, y naught, and z naught. That is this. To define delta ball in a higher dimension, add additional terms under the radical to correspond to each additional dimension. For example, given a point P, W naught, X naught, Y naught, Z naught in R to the power of 4, a delta ball around P can be described by this. So we still call it ball in higher dimension. To show that the limit of a function of 3 variables exists at a point, it suffices to show that for any point in a ball centered at x naught, y naught, and z naught, the value of a function at that point is arbitrarily close to a fixed value. All the limit laws for functions of 2 variables hold for functions of more than 2 variables as well. Finding the limit of a function of 3 variables. Before we can apply the quotient law, we need to verify that the limit of the denominator is non-zero. 4, 1, minus 3. Okay. Since it's not non-zero, we next find the limit of the numerator using the product law, the difference law, constant multiple line identity law. Last, applying the quotient law, we are left with 25 over 16. Okay, I will just read the next chapter. Most of the practicing will be done off stream. Just read the next chapter and yeah, I will end the stream there. How much is left? I think it will take like 2 or 3 more streams to finish this. When studying derivatives of functions of one variable, we found that when interpretation of the derivative is the instantaneous rate of change of y as a function of x, Leibniz notation for a derivative is dy over dx, which implies that y is the dependent variable and x is the independent variable. For a function c is f of x, y of 2 variables, x and y are independent variables and c is the dependent variable. This raises 2 questions right away. How do we adapt this notation for functions of 2 variables? Also, what is an interpretation of the derivative? The answer lies in partial derivatives. Let f of x, y be a function of 2 variables, then the partial derivative of x with respect of x of f with respect to x written as delta f over delta x or fx is defined like this. So they're finding the derivative for a fixed y. Partial derivative of f with respect to y is defined like this. This definition shows 2 differences already. First, the notation changes in the sense that we still use a version of the Leibniz notation, but d in the original notation is replaced with delta. This is rounded d. This rounded d is usually called partial. So, partial of f with respect to x. This is the first hint that we are dealing with a partial derivative. Second, we now have 2 different derivatives we can take since there are 2 different independent variables. Depending on which variable we choose, we can come up with different partial derivatives altogether and often do. Use the definition of the partial derivative as a limit to calculate delta f over delta. Wait, what is it? Partial of f with respect to x. Partial of f with respect to x and partial of f with respect to y for this function. Hold on. Let's try this. So this is 4.14. F of x is all of this. Let's write it here. F over, what's the notation they use? Is it called delta? What is this? I don't think it's delta. I've been saying delta for so long. X. We derivate only the x part, right? Limit as k approaches, as h approaches 0. Now what? Limit as h approaches 0. I don't think we are doing this right. But let's just see. Minus 3xh y. I don't think this is correct. Do we like just derivate all the x part? So x squared will become 2x. This will become minus 4, and then this will, what will happen to this though? I think it will just remain 3y, maybe. If I do minus f of, hold on. If I do minus f of xy, some parts will cancel out, right? So this minus 12 will cancel out, 5y will cancel out. This will remain, so this will remain. For x, 2y will cancel out. And then minus 3, this will come plus 3xy. So when we put this in, we get this. Let's see. And what about this? Minus x squared. Yeah, I forgot that. So minus x squared plus 3xy plus 4y. Sorry, plus 4x. Yeah. If we bring h very close to 0, this and this will cancel out. Now, if we bring h very close to 0, this and this will cancel out. So we are left with these two minus 3x plus hy. And then I can expand this and write 3xy minus 3hy. This and this will cancel out. I'm left with minus 3y. I don't even know if this is correct. Wait. For this part, minus 4x plus h. If we expand this, we are left with minus 4x minus 4h minus 4h. So the x part will cancel out, the h part will remain. So 4 survives. And then over here, this is expanded into, hold on. Let me just clear this up. So x squared plus 2xh plus h squared 3xy minus 3hy plus 3xy minus 4x minus 4h plus 4x. Yeah. So let's see which ones cancel out. This and this cancel out. So we are left with 2xh plus h square. This and this cancel out. Four x will cancel out. And then we are left with 2x plus h minus 3y minus 4. And then as h approaches 0, we are left with 2x minus 3y minus 4. 2x minus 3y minus 4. Okay, so I was confused mainly about this part. So I'm going to guess what happens with y, with respect to y. You're going to have wait, I forgot to add minus plus 2y square. Hold on. So I have this, this, this. Oh no, but it would be cancelled out, right? That's why I didn't add it. Anyways, I think I will end up with minus 3x plus 4y plus 5. Yeah, minus 3x plus 4y plus 5. Isn't it the same as treating one variable as a constant? Like if I treat x as a constant and then derivate it with respect to y, I get the same answer. The idea to keep in mind when calculating partial derivatives is to treat all independent variable other than the variable with respect to which we are derivating as constants. Then proceed to differentiate as with a function of a single variable. To see why this is true, first fix y and define g of x is f of xy as a function of x. Then you do this. This is same as true for calculating partial derivatives of f with respect to y. So over here, with respect to x, we will have, isn't this the same thing? Okay, for this, we will have derivative of the outside. So it will become cos x square y minus 2x plus 4. And then derivative of the inside, 2xy minus 2. Hold on, what? 2xy minus 2. Derivative of the outside and the derivative of the inside. So they're derivating x, 2xy minus 2. Yeah, I'm correct. How can we interpret these partial derivatives? Recall that the graph of a function of two variables is a surface in R cubed. If we remove the limit from the definition of partial derivative with respect to x, the difference quotient remains. This resembles the different quotient for derivative of a function of one variable except for the presence of a y variable. Figure 4.21 illustrates a surface described by an arbitrary function c is equal to f of xy. In figure 4.21, the value of h is positive if we graph f of xy and f of x plus hy for an arbitrary point xy. Then the slope of the secant line passing through these points is given by this. Use a contour map to estimate this at a point root 50 for this function. Hmm, hold on. This line is parallel to the xc plane. Therefore, the slope of the secant line represents the average rate of change of a function as we travel to the x-axis. As h approaches 0, the slope of the secant line approaches the slope of the tangent line. If we choose y instead of x by the same incremental value, then the secant line is parallel to the y-axis, and so is the tangent line. Therefore, if x represents the slope of the tangent line passing through the point xy, f of xy parallel to the x-axis, and f partial derivative of f with respect to y, it represents the slope of the tangent line passing through the point xy, f xy parallel to the y-axis. If we wish to find the slope of the tangent line passing through the same point in any direction, any other direction, then we need what are called directional derivatives. We now return to the idea of contour maps, which we introduced in functions of several variables. We can use a contour map to estimate partial derivatives of function g x y. Okay. Following graph represents a contour map for a function g x y. So root 9 minus x square minus y square. The inner circle on the contour map represents to c is equal to 2, and the next circle out corresponds to c is equal to 1. First circle is given by the equation 2 is equal to root 9 minus x square minus y square. The second circle is given by the equation 1 is equal to root 9 minus x square minus y square. The first equation simplifies to x square plus y square is 5. Okay, and the second simplifies to this. The x-intercept of this first circle is root 5, 0. And the x-intercept of the second circle is this. We can estimate the value of partial derivative of g with respect to x evaluated at the point root 5, 0 using the slope formula. To calculate the exact value of partial of g with respect to x evaluated at the point root 5, 0, we start finding partial of g with respect to x using the chain rule. First, we rewrite the function as this, then we differentiate with respect to x while holding y constant. Next, we evaluate this expression using x is equal to root 5. The estimate of the partial derivative corresponds to the slope of the secant line passing through the points root 5, 0, g root 5, 0 represents an approximation to the slope of the tangent line to the surface through the point which is parallel to the x-axis. Okay, functions of more than two variables. Suppose we have a function of three variables such as w is equal to f of x, y, z. You can calculate partial derivatives of w with respect to any of the independent variables simply as extension of the definition of partial derivatives of functions of two variables. Let f of x, y, z be a function of three variables, then the partial derivative of f with respect to x written as partial f with respect to x is defined to be this. The partial derivative of f with respect to y written as this is defined to be this. Okay, you can calculate a partial derivative of a function of three variables using the same idea we used for a function of two variables. So calculating partial derivatives for a function of three variables, use the limit definition of partial derivatives to calculate partial f with respect to x for a function. Then find partial f with respect to y and partial f with respect to z by setting the other two variables constant and differentiating accordingly. So if we want to find x with respect to x, we would do 2x. We would get 2x minus 3y plus, no, not this is removed, minus 4z minus 12. Yeah, that's it. 2x minus 3y minus 4z minus 12. Calculating partial derivatives for a function of three variables. Calculate three partial derivatives for the following function. Okay, for let's do b just for x. So for this one, it would be derivative of the outside. So cos x squared y minus c, and then the derivative of the inside would be, which will be 2x. Then over here, it would be a minus sine x squared minus yz, and then the derivative of the inside would be 2x. C, B, hold on. We are B should be over here. So 2x, sorry, this should be 2xy cos x squared y minus c. Higher order partial derivatives. Consider the function f of x, y. Its partial derivatives are partial of f with respect to x, partial of f with respect to y. Each of these partial derivatives is a function of two variables, so we can calculate partial derivatives of these functions. Just as with derivatives of single variable functions, we can call these second order derivatives, third order derivatives, and so on. In general, they are referred to as higher order partial derivatives. Uh, there are four second order partial derivatives for any functions provided they all exist. So, okay, so like partial derivative. So, what do we call this? Like, so higher order with respect to x, and then x again, x then y then x, and then y twice. An alternative notation is fxx, fyx. Yeah. Higher order partial derivatives calculated with respect to different variables are commonly called mixed partial derivatives. Calculate or for second partial derivatives for the function. Uh, okay, actually, let's hide the solution and let's do this actually. So we have 4.19. Calculate or for second partial. Let's just do x then y. So partial of f with respect to x would be, this is treated as a constant, so then plus derivative of sine is cos, and then derivative of inside, which is 2. Now, we do all this. Derivative of this, derivative of the outside times the derivative of the inside, minus 3, and then plus derivative of all this. Derivative of cos is minus sine, so this will be minus sine 2x, and then derivating the inside with respect to y will be left with a minus 5, so this will become plus 10. So this was, we derivated x, then y. It's x, then y. It's minus 3 e to the power of minus 3y plus 10 sine 2x minus 5y. Okay. Suppose that f of xy is defined on an open disk that contains the point AB. If the function xy and if the function fxy and fyx are continuous on D, then the two are equal. Hold on. How do you pronounce this? Clairaut theorem guarantees that as long as mixed order derivatives are continuous, the order in which we choose to differentiate the functions does not matter. It can extend to higher order derivatives as well. Two of the second order partial derivatives can be calculated for any functions. Partial derivatives is equal to the partial derivative of x with respect to x, and fyy is equal to the partial derivative of y with respect to y. In the introduction to differential equations, we studied differential equations in which unknown functions had one independent variable. A partial differential equation is an equation that involves an unknown function of more than one independent variable and one or more of its partial derivatives. Examples of partial differential equations are so we have ut is c squared and then these two partial derivatives, then wave equation, then Laplace equation in two dimension. The first two equations, the unknown function u has three independent variables t, x, y, and c is an arbitrary constant. The independent variables x and y are considered to be spatial variables and the variables t represent time. In Laplace's equation, the unknown function u has two independent variables x and y. Why does it look like this? Verify that this is the solution to the wave equation. So this is wrong. This, I don't know why it doesn't copy properly. So UXYT sample 4.20. Five sine 3 pi x. Sine 4 pi y cos 10 pi t. So this with respect to x. So what are we doing? X with respect to x. There's no x here. There's no x here. There's only x. So all this would be treated as constant, right? So 5 sine will become cos. And then we do it again. This time 3 pi itself is also constant, right? So 5 times 3 is 15 pi. Then this will be minus sine 3 pi and then 3 pi outside. No, wait. Minus sine 3 pi x and then 3 pi. And then now we have to do it with y. So all this, so everything is treated, almost everything is treated as constant. And now we differentiate this. This becomes cos 4 pi y and 4 pi. This with respect to y. Uh, sorry, u. Uh, now it works. So 4 times this and then we have to do t and t as well. 5 sine 3 by x. Is it sine and sine? It is. Sine 4 pi y. Cos becomes minus sine 10 pi t. So now what? We have sine 3 pi x, sine 3 pi x over here. What? Okay, what can we extract? So if we have x, x again, plus it with y, y again. We have, let's see, we have this and this. Let's see the common terms. Sine for 4 pi y. Yeah, this is common. Or the, okay, we have sine 4 pi y sine 3 pi x cos 10 pi t. Then we have pi on both sides. So pi square. Now what? Now these are the different ones. Hold on. What was it? What was it? 45? 3 times 45 plus 80. Right? Mm. And then we can extract 4 out. But what would we be left with? 80 plus 40 is 120. 120. Now what? If we extract 4 out, this would be 30. But this is not equal to this. I made a mistake somewhere. 15, 20. Why is this over here 80? 5 and 50. Okay, this becomes 50. If we differentiate again, this becomes this, and then there is 10 pi, so it actually becomes 500, which is not correct. Okay, this is correct, minus 500, right? Then what about this? 5 and 4, 20, 4 and 20, 80. No, 4 and 20 is 80. That's correct. 3 and 15 is 45. Hold on, maybe the first one is the issue. Okay, is it 80? Is 80 correct? Minus 80 minus 45. Those are correct. I think the issue is here then. Minus 80 minus 45. We got minus 80 and minus 45. Minus. This is a minus 125. Minus 125 times 4 is Okay, then I got it right. Yeah, that took so long. Since the solution of a two-dimensional heat function is a function of three variables, it is not easy to create a visual representation of the solution. We can graph the solution for fixed variable of t, which amounts to snapshots of heat distributions at fixed times. These snapshots show how the heat is distributed over a two-dimensional surface as time progresses. The graph of the preceding solution at time t is equal to 0 appears on the following figure. Should I read all this? Okay, I will just read it off stream. Oh no. During the late 1800s, the scientists of a new field of geology were coming to the conclusion that Earth must have been millions and millions of years old. At about the same time, Charles Darwin had published the treatise on evolution. Darwin's view was that evolution needed many millions of years to take place, and he made a bold claim we that wheeled what wheeled chalk fields, where important fossils were found, were results of 300 years of erosion, million years of erosion. At that time, eminent physicist William Thomson Lord Kelvin used an important partial differential equation known as the heat diffusion equation to estimate the age of the Earth by determining how long it would take Earth to cool from molten rock to what we had at the time. His conclusion was a range of 20 to 40 million years, but most likely about 50 million years. For many decades, the proclamation of the irrefutable account of science did not sit well with geologists or with Darwin. Kelvin made reasonable assumptions based on what was known in his time, but he also made several assumptions that turned out to be wrong. One incorrect assumption was that Earth is solid and that cooling was therefore via conduction only, hence justifying the use of the diffusion equation. Uh, but the most serious error was a forgivable one: omission of the fact that Earth contains radioactive elements that continually supply heat beneath Earth's mantle. The discovery of radioactivity came near the end of Kelvin's life, and he acknowledged that his calculation would have been modified. Kelvin used the simple one-dimensional model to applied only to Earth's outer shell, derived the age from graphs and roughly known temperatures gradient near Earth's surface. Let's take a look at a more appropriate version of the diffusion equation in the radial coordinates, which has the form this. Okay, I will read the. Wait. On May 20, 1904, physicist Ernest Rutherford spoke at the Royal Institution to announce a revised calculation that included the contribution of radioactivity as a source of Earth's heat. In Rutherford's own words, I came into the room, which was half dark, and presently spotted Lord Kelvin in the audience and realized that I was in for trouble at the last part of my speech dealing with the age of the Earth, where my views conflicted with his. To my relief, Kelvin fell fell fast asleep, but I came to the important part. I saw the old bird sit up, open an eye, cock a baleful glance at me. Then a sudden inspiration came, and I said Lord Kelvin had limited the age of the earth provided no new source was discovered. The prophetic utterance referred to what we now considering tonight. Radium, behold, the old boy beamed upon me. Rutherford calculated an age of Earth about 500 million years. Today's accepted value for the of a Earth's age is about 4.6 billion years. Okay, I will end the stream here then. And yeah, I will continue studying this next stream, I guess. Okay, anyways, see you guys next time. Bye.